In this video, we're going to start to take a look at dynamic programming. Dynamic programming is typically seen as an extension to the divide and conquer approach. In divide and conquer, we divided a problem into smaller subproblems, then we solved those subproblems and combined back into the solution to the main problem. With dynamic programming, we're considering cases where when we divide into smaller subproblems, some of those smaller problems may overlap with each other. So they may be the exact same as each other. In those sorts of situations, if we took a dynamic programming approach, we'd be able to remember the solutions that we've seen rather than having to recalculate them. So in divide and conquer, we would have to calculate every single solution, even if they're the same problem. However, with dynamic programming, what we do is on each division, we solve our problem, we store that result, and then if we see it in the future, we simply use the result we stored instead of recomputing a solution. And to understand why that's really important as an approach, I want to show you a simple problem known as the climbing stairs problem. The idea behind this problem is that you have a set of stairs that has n steps in it. You can climb either one step or two steps every single time until you reach the top of the stairs. The question is, how many unique or distinct ways can you climb to the top of the stairs? So I'll give you an example. Suppose that you were to have, say, 3 steps. If you had 3 steps, there are really 3 different ways that we can climb up the steps, right? We could climb up 2 steps and then 1 step, makes 3 steps, right? We could climb up 1 step and then 2 steps. Or we could climb up 1 step, 1 step, and 1 step, right? Those are the 3 main ways that we can manage to climb up these stairs. So in this case, the answer would be 3. And you see that we can basically rephrase this question of how many different ways can we sum to a value n using the numbers 2 and 1 as many times as we would like, right? That's sort of the idea of this. And in this sort of problem, basically, there's a really simple sort of looking code to solve this, right? What we could do is we could say something like this. So we could say climb stairs with n. We could say if n is equal to 0, or if n is equal to 1, we would return 1. Otherwise, we could just return the value of climb stairs at n minus 1 plus climb stairs at n minus 2, basically saying the different combinations of 1 step and 2 steps, right? This would generally solve our problem. And I could show you that, if I plug in any sort of, 1 here, say for instance 3, the example that we had, right? We would see that it does actually produce to us a pretty reasonable solution, right? So we see that we get the value 3 as a result, right? Which is exactly what I said would be the answer for this. And if we get up to values like 5, for instance, we'll see that this continues to grow, right? We get like 8 solutions in this case, and then it will continue to grow from here. So this solution seems to work, but what generally is the problem here? Well, this solution is very slow, right? Because it turns out that as we follow through the recursion of this, we actually find that this is going to be O2 to the power n, which is a really, really bad time complexity. Basically, this, if n gets large enough, will never actually finish, right? And you could try it. You could start putting in larger values of n, and you'll find that the solution actually takes quite a long time to compute, right? So, if I put in, say, 100, I'm generally going to notice that it's going to be, fairly slow overall. So let me just put in my value here. Here we go. Do you see how long this is taking to compute? And generally, I'm not even really convinced that at 100, it's actually going to end, right? You see, this is taking an extremely long time to happen. Even before this value, as we get up to 10, it takes a bit of time to actually compute, right? So you're going to start to see that as n grows larger, and large is actually not even really that big, it starts to really slow down. So this is a significant problem for us. So the question is, how can we do better? Well, what you'll notice in the 3-step example is that we have some repetition, right? So 1 plus 1 plus 1 is unique, but 2 plus 1 and 1 plus 2 are the same thing, right? Because addition works in both directions, right? It doesn't matter if it's 2 plus 1 or 1 plus 2. These 2 problems are the same as each other. So we could have remembered these solutions and cut us down to just having to do basically 2 computations, just these 2 here. And that just becomes bigger as we grow the value of n. The number of repetition in the actual solutions becomes very large, right? So we could take an approach to try to remember some of the different solutions that we've seen. There's two main approaches that dynamic programming uses for this. The first is top-down, and the second is bottom-up. Top-down is sometimes referred to as memoization. And basically the idea behind memoization is that we're going to start computing at the top, so at the largest value of n, and we're going to store the results each time, and then we're going to use those results as a result in our next iteration. So basically we could start at, for instance, if n was equal to 5, we'd start at 5, then we'd do 4, 3, 2, 1, and we continue storing the results as we continue down that path. This ends up being recursive as well, and generally what you'll see is that it looks something like this. We can have our starter of climb stairs at n, and it's going to declare basically a way of remembering the solutions, which I'm going to call my memo. And I'm going to declare my memo as a dictionary. Two different ways to do that. We can use the brace brackets here, or we can use the dictionary notation like this. And then I'm just going to return the result of my climb stairs auxiliary function, which is going to handle all of my recursion. The reason why I do this is because I have to initialize the memo. If I were to initialize the memo and have the recursion inside of the same function, I would end up overwriting the memo each time, which would kind of defeat the purpose of it, right? So we have n and memo, and we do a similar sort of approach. If n equals 0 or n equals 1, well, we just simply return 1. And then we say if n is not in the memo, then we're going to store the result of running the climb stairs auxiliary at n minus 1 with the memo, plus the result of doing it at n minus 2 and the memo, right? And then simply at the end of this, all I do is I just return memo at n being the value that we were looking for the solution at, right? So do you see here that really all that changed was that rather than just doing this recursion, we do this recursion and store the result inside of a dictionary for us to be able to retrieve the results later. We use a dictionary because the lookup in that dictionary to find the value n is fast, right? This generally is going to be constant time to check if n is in the memo, which makes it very easy for us to actually, validate that without having to do extensive computation. This completely changes the amount of time it takes for us to actually compute a solution, right? So in this case here, we actually get a much better time complexity, right? So if I do this again with stair step, what you'll see is that generally it completes pretty fast, and we can probably get ourselves up to 100 now, and we're not going to end up with it sitting forever. Do you see now that we actually get a solution basically instantly? This is a significant change. We went from solving the problem at all, right? Not being able to solve it at all to actually having a solution. So this is a very important difference, right? We look at this sort of solution here and we see that it's pretty good. And generally recursion is kind of something that we want to try to avoid in a lot of cases. We've used it a few times throughout this course so far, but if we can avoid using recursion, I like to try to avoid it because recursion is a bit complicated to understand. It takes up a bit of memory because we have to store every function call in memory on the recursion stack, and that in turn lowers our efficiency a little bit. So in order to remedy for this, there's actually another approach that we can take for this sort of problem, which is a bottom-up approach. A bottom-up approach is going to remove recursion, and it's actually going to give us a bit of a cleaner sort of result. So what I'm going to do is I'll end this video here. We've seen the general sort of naive approach, and then we've seen this top-down memoization approach. In the next video, I'm going to show you the bottom-up approach, and we'll discuss a little bit about that solution. So thanks so much for watching, and I'll see you in the next video.